Hello. Hello. Yeah, shall we start?
Yes, sir.
Okay. So the next topic we are going to start is nomenclature of coordination compound. Okay. So nomenclature, like we did in organic chemistry. Here we have some rules. Okay. So we'll follow those rules to write down the name of these compounds. Right. So like if you are going to write down the rules one by one, it will take a lot of time. So I'll just show you for the reference for now. Okay. And that PDF I'll share with you. So you can copy those notes later on, those points later on. Okay. So we'll continue with it. Right. So let me just show you. I'm just stop sharing my screen for a while and then I'll come back. Just a second. Okay. Now you see this. These are the rules we have of nomenclature. Right? We'll just go through it quickly. And this PDF, this PDF is for the entire chapter. Okay, the entire chapter is given here, and there are some solved questions also which you can practice later on once we finish the chapter. So I'll share after the session the entire PDF with you. Okay, here we'll focus just on the rules which is given here: A, B, C, D. All these rules. See, all these rules. If I'm going to dictate you, it takes a lot of time. Okay, that's why I'm skipping this. But these rules you must write or keep these notes properly if you don't want to write the rules, because you have to revise it at times. Okay. See, the first rule is very simple. We'll name the compounds like we name the simple salt. Positive part first, and then the anion in the last. Like sodium chloride, Na plus will write first, sodium and then chloride. Here also, if you have positive part is this, then potassium and then the name of this complex, FeCN6. Okay, that is what written over here. Naming with the complex, it starts with potassium. Here, the complex cation it is. So we'll write down the name of cation first, that is the complex part, and then we'll write in the last with space chloride. Okay, the name of this complex starts with the name of complex ion, which is this. Means whatever positive ion is there, we'll write down the name first. K4FeCN6 here, we'll write down the name of this first. What we say, name of ligands first. Okay. First, we write down the name of ligands, then we metal. Then we write down the name of the metal. And just after the name of the metal, we'll write down the oxidation state of the metal in parentheses. Okay, I'll show you some examples, we'll get it. Okay. If you have multiple ligands, more than one ligands present, then we'll write down the name of ligands in alphabetical sequence. Right? That's the basic rule we are following here. But how do we write down the name of ligands? So that to write down the name of ligands, we have certain rules here. You see, the ligands can be neutral, anionic, or cationic. So if it is neutral, we have one particular rule type of name, anionic, one particular type of name, cationic, one particular type. So this you must go through once properly. Okay. See, it is written here. Neutral ligands are named as the molecules. Like you see, C5H5, when it is pyridine, so we'll write on pyridine. C5H5 whole thrice triphenyl phosphine, no change in this. This one, ethylene diamine, no change in this. Neutral ligands which are not named as the molecules are CO as carbonyl, NO as nitrosyl, H2O as aqua, NH3 is amine double M. Must take care of it. Okay. This one point, the first point is very important. In fact, this C, the point number C, you have to go through properly. It's very important, right? The neutral ligands named as the molecule, but these are some different names we have. CO is carbonyl, NO is nitrosyl, H2O is aqua, NH3 is amine, A double M. Okay, not single M, double M. Anionic ligands ending with ide are named by replacing ide with O. Means ide ka ito ho jayega, right? Ide becomes ito, ate becomes ato, ite becomes ito. So suffix O we have to add for anionic ligands. Okay, for anionic ligands, right? Anionic ligands, ide, O suffix you need to add. For example, you see Cl minus is chlorido or chloro chalta hai. Br minus is bromo or bromido. Cn minus is cyano. O2 minus oxo. OH minus hydroxo. N3 minus nitrido. O2 2 minus peroxo. O2 H minus perhydroxo. S2 minus sulfido. Like this it is given, you can go through once. Okay. So next we'll see. Okay. OH minus hydroxo, NH2 minus amido and all. Ligands with the name end in ite or ate becomes ito by replacing ending E with O as follows. Carbonate, carbonato. Oxalate, oxalato. Sulfate, sulfato. Like that. Acetate, acetato. Okay. Then for positive ligands, you see we have third point. Positive ligands ending with EM suffix. So hydrazinium, nitronium, okay, nitrosonium, NO plus. Okay. Now this is the name of the ligand point number C, which is different from what we did in the nomenclature previously. So this point number C you must take care of. Now if ligands are present more than one, then repetition is indicated by prefix di, tri, tetra, etc. However, when the name of the ligand includes a number, dipyridyl, ethylene diamine, bis, tris, tetrakis are used in place of di, tri, tetra. I'll discuss this example in just a second. With example, you will understand. Here you will get confused. Okay, if ligand is already contains prefix like ethylene diamine, or if it is polydentate ligand, then prefix bis, tris, or char. The same thing we'll discuss it. More than one type of ligand, alphabetical sequence you need to follow. After naming the ligands, the central metal ion to be named immediately, followed by this oxidation state in Roman under the brackets as per IUPAC. Okay, in parentheses. Okay. NH2, NH4, 2CuCl4. So NH4 will write down first because always cationic part first. Ammonium. Okay. 4-chlorine tetrachloro, then cuprate. If it is negative, if the metal is in negative part, negative anion, then 8 will write down cuprate, and then oxidation state of copper 2. After naming the central metal atom, ion which is in the order outer sphere is to be named. The naming of the sum of the complexes is done as follows as per IUPAC. Okay, fine. Now with example you'll get it. See this one. K4FeCN6. So positive part is potassium. So potassium hexacyanoferrate. Negative ion, so ferrate. What is the oxidation state? +2. So we'll write down +2 in the Roman. Potassium hexacyanoferrate. You see +2 here. Number 2, K2PtCl6, positive part. Potassium hexachloroplatinate. Platinate. +4 is the oxidation state. Here we'll write down the positive part first. This part will name first. And in the complex part, we'll write down the name of ligand first and then metal. The ligand is hexaamine, A-double-M. Take care. Hexaamine, A-double-M. Right? Cobalt 3 chloride. Right? One more point was there. I did not. Ethylene diamine was a point where we use single M in the spelling. Okay, I'll see that. Now you see CrH2O4Cl2Cl. This will write down first two ligands we have here. So this H2O, the name is aqua, it is chloro. So first we'll write alphabetically aqua and then chloro. So tetra aqua dichloro chromium, oxidation state of chromium is 3. So tetra aqua dichloro chromium 3 chloride. Right? This one. It is amine chloro, right? So diamine double M tetrachloro platinum, oxidation state is 4. Triamine trichloro cobalt 3. Okay, like this will name. Did you get it? Any doubt in this? Little bit of idea you have. I'll give you some examples now. Okay, we won't go like this. But did you get it? This 4-5 points that I've discussed now.
Yes, sir.
Yes, sir.
We'll discuss some examples because without example you won't get it. Okay, let's discuss some examples. And I'll share this PDF. Okay, don't worry. Okay. Now suppose the compound is this, which you have to write down the name. And the compound is this one. CO NH3 4, then H2O Cl bracket close Cl. This is the first one. Second one is Cu En2 SO4. Ni CN4 2 minus. Try this. Done. Okay, I'll do the first one. So positive part first. So first we'll write down the complex part in the first one. Acha, wait. So we have this thing 1, 2, 3, 3 ligands here. So this one is amine, this one is aqua, and this one is chloro. So first we'll write down A wala ligand, right? So A and A. Amine, aqua, first we'll write amine, right? Alphabetically. So the name of this compound is tetraamine, TETRA, and A double M, not single M, tetraamine, then aqua for water, then chlorido you can write, or you can write chloro, cobalt. What is the oxidation state of cobalt? It's -1. So this one is +1. This is -1. This is 0. This is 0. So it is +2. Yes or no? Cobalt. Then in the bracket, the oxidation state, chloride. Is it fine? Okay. This one I'll do in the last. Wait for it. This one is tetracyanonickelate. Nickelate. Oxidation state of nickel is +2 here. So nickelate 2 ion, because it is not a molecule, it is an ion. So nickelate 2 ion. Okay. Now this one you see the Bistris wala rule will use over here. The name of this ligand is what? Ethylene diamine or ethane 1,2 diamine. Okay. It is ethane 1,2 diamine. So the name of the ligand already contains di term with it, like ethane 1,2 diamine. So when the name of the ligand contains a term like di, tri, tetra, or like that, then for these numbers, we do not use again di, tri, tetra word, but we use bis, tris, tetrakis like that. Okay. So if it is 2, so we'll write down for this ligand, we'll write down bis, okay, bracket open, ethane 1,2 diamine, ethane 1,2 diamine, bracket close, copper, oxidation state of copper is 2, copper 2 sulfate. Did you understand this? One more point that you have to take care of here, that when it is amine, means monodentate ligand, then we are using double M here. But when it is this polydentate ligand, then we're using single M here. Okay. If the complex part is positive ions and neutrals, then there's no special ending. We'll write down the name as it is. But when the complex is negative ions, we'll write down 8 suffix like I have written here, nickelate. Other examples also I have shown you. It is 8 suffix we have added. Okay, got it? Some more examples I'll show you here. Wait. This one you do. COEN3 SO4. CO, ONO, NH3, SO4. Another one, Li, ALH4. Try these compounds. Yeah, I'll do it. Shashank, this is it. This one is Shashank, get out. This one. The name of this compound is ethylene diamine, right? So for this three, we'll write down tris. We don't write tri here because the name itself contains diterm. So we don't write tri, we'll write down tris. Open bracket, ethane, 1, 2, diamine with a single M, cobalt. What is the oxidation state of cobalt here? It is 2, then space and sulfate. Okay, this one is the oxidation state. If you see, it is 0 and NO2. What is the oxidation state here? NO2, what is the charge?
-1.
-1, right? So cobalt will be +3 because it is -2, and on the complex we have +2 then. So this one is, it is pentamine, and this one is nitrito O. ONO it is written. It means oxygen is a donor atom here. So nitrito O will write. If NO2 simply it is written, then nitrogen is the donor atom. Okay. So name of this compound is pentamine. Pentamine, AMMINE, pentamine. Then the another ligand is nitrito O, cobalt. There's no space here. Okay, cobalt 3 sulfate. LiAlH4 is lithium. What we should write the positive part first. Lithium is fine, but tetrahydrido is correct. Yes, and lithium and then space tetra, because it is hydride ion, right? So it is negative ion. So hydride I becomes ido. Tetrahydrido aluminate because the negative ion. Oxidation state is, what is the oxidation state?
3.
This is 3. It is. We have Li plus and AlH4 minus. It is a negative ion. Right? So this, like this, we'll write down the name. Okay, I'll share that PDF. To solve some more questions, you'll have the idea of it, how to do it. Just you need to follow the rules. Okay?
Sir?
Yeah.
Sir, for organic reactions, this gives hydride ion, right?
Ah,
Sir, but the complex doesn't dissociate, so how does it give the hydride ion?
okay, complex. See, in organic reaction, we have different conditions. No, we are talking. It's not like you cannot break this. Right? It is not like you cannot break this.
Yes, sir.
What we are talking about that when you dissolve this in water in aqueous solution, then this part retains its identity. So I said what? That the complex part retains its identity in solution, right?
Yes, sir.
But in organic reaction, we have elevated temperature, right? High temperature we are using. We are using this reagent in order to provide hydride ion, correct? So for that purpose, we use the necessary condition which is required.
Yes, sir. Got it, sir.
It's just we are talking about in solution it retains its identity.
Yes, sir.
Yeah.
Yes, sir.
Yeah. One second. Okay. Now in this nomenclature, you see in some of the question they'll give you both part cation and anion part complex. So in that case, you have to understand how to write down the name. Okay. Suppose we have this, not much important, but we'll see just one example. CrNH3 and the another one we have COCN6. COCN6. Correct? So the name of this compound I'll write down first. It is hexaamine because always we'll write down the positive part first. So hexaamine, chromium, oxidation state you let it be now. Then some space, hexacyano, cobalt, cobaltate, oxidation state we'll see. Okay. So oxidation state, how do you assign? That's the thing, right? What you do, you just find out the total charge. What is the total charge we have? NH3 we have 0, no charge on NH3, and Cn has -1. So total charge is 6, like the magnitude 6. So this charge you have to distribute equally on the two metal. So we'll write down 3 here and 3 here. This is the name of this compound. Try this one more I'll just give you. PT NH3 4 CuCl4. Done. So it is tetraamine platinum 2 tetrachloro cuprate 2. Is it? Yeah, that's right. Okay, the name is tetraamine platinum 2 tetrachloro cuprate 2. Okay, if you are doing this, these kind of questions in the exam, then you don't have to name this like this. Okay, I would suggest first of all you find out the oxidation state of the metal, whether it is both complex or the normal one that we were doing before this, right? Find out the oxidation state first. Okay, especially when you look at the option, and if you see the oxidation state differs in all the options, then you just find out the oxidation state. According to that, you can remove the options easily, eliminate the options easily. Okay, so nomenclature questions, basically, it's not a good idea to solve this way. Like you find out the name and all these things and write down the name and then compare with the options. You can easily eliminate options there. Okay, now next thing is sometimes what we have bridging group ligands. Okay, bridge ligands are present. I'll show you how it is. For example, you see this one. Just we are looking at one example because these things are not at all important. Okay, H2O4, then we have Fe, and there is a ligand which acts as a bridge here, OH, and it is connected to Fe here, H2O 4 times and SO4 like this. SO4 whole twice. SO4 whole twice. So how do we write down the name of this? You can write down this as like separately, this part and this part you can write down, or you can also write down, because we have two bridge like this, so we'll use bridges 2, so we'll use di for that. Di, and we'll use a Greek word mu to represent the bridging ligand here. Mu means it is a bridge group ligand. Okay, we have these things are written in the rules. Okay, it is not given in that particular PDF because it is not important. Okay, but I'm giving you just one, two example I'm discussing so that you can do it. Hardly I have seen this kind of question they have asked in the exam. Okay, mu represents the bridging group ligand. Okay, mu, and then 2-hydroxy we have here, right? So di means 2-hydroxy, mu means bridge. Then we'll write hydroxo. Then we'll write down, we have H2O4 twice. So we'll write down bis. The name of this is tetra aqua. Iron. Oxidation state of iron is, you see, -1 here, -1 here, -2 into 2, -4, so +4 here. +4 + 2 + 6, we'll divide this +6 equally on the two metal. That is 3. Okay, bracket close, tetra aqua. I'll write down one bracket here also because this is for this tetra aqua. No, just a second. No, we have this one. No, one second. Di mu hydroxo, we have done with this, and then this part we'll name it as bis. Yes, bis tetra aqua. Okay, bis tetra aqua iron 3, and then sulfate. This is the name of this compound. Mu, we use a Greek letter just to represent the bridging group ligand. Okay, I'll give you one point here, one note you write down. In this one note you write down the bridging ligand is expressed by Greek letter mu. I'm repeating myself. Bridging ligand is expressed by a Greek letter mu, which is added immediately before the name of the ligand and separated by a hyphen. Name of the ligand and separated by a hyphen. Okay. No, disulfate we don't put. Disulfate we don't put. Simply we'll write down sulfate, because when you write bis tetra aqua iron means there are 2 iron atom present, right? To balance that, we should require 2 sulfate. So from there you got the idea that we'll have 2 sulfate ion. So that is not required.
Sir, could you just repeat the last part of what you said?
The point that in the note, right?
Yes, sir.
Yeah, I'm repeating myself. The bridging ligand is expressed by Greek letter mu, which is added immediately before the name of the ligand and separated by a hyphen. Okay. Okay, one more example on this will do, and then we'll move on. You can have 2 different bridging ligand also. Here we have OH, so I've written dimu hydroxo. If you have 2 different names, then you can write down the name of the 2. Like you see this one. NH3 whole 4. Then we have cobalt NH2. NH2 NO2 cobalt, then NH3 4, and then we have nitrite NO3 4. Sorry. Try this one.
So NH2 is imine?
Sorry?
So what is NH2?
NH2. NH2 is amide. No, so amido you can write. NO2 is nitrate.
So the bridge is like 3 center 2 electron bond kind of thing.
Bridge 1.
Yes, sir. So because it's not a didentate ligand, sir.
Yes.
So
Because
it's like
yeah, it's like 3 center 2 electron, because NH2 already has only one lone pair. No? So it
Yes.
is distributed among the 3 nucleus, NCOCO.
Okay, sir.
So see, here we have two different bridging group ligand, right? One is amido, NH2, other one is nitrito, NO2. So we'll write down mu 2 times here. Okay. So the name of this compound you see, it is nitrito, it is amido. Alphabetically, we'll write this first. So we'll write down mu amido. This means the NH2 group is present as a bridge here between the two metals. Then one more we have, so mu nitrito. Oh, here we have a small n here, right? Small n, nitrito. Okay, then we have 2 times here, tetraamine. So we'll write down bis, open bracket, tetraamine, cobalt. What is the oxidation state? What is the charge?
3.
Nitrate. Tell me the charge here. NO3
3.
minus, NO3 minus, so 4 minus, so 4 plus on this, right? Minus 1, minus 1. So plus 6 divided by 2. Plus 3 will have.
Sir, we should write nitrito N also. Nitrito N.
Iron why will write? Because it's a molecule, no?
So no, sir, nitrito
Please.
N I meant for the bridging ligand.
Nitrito. Oh no, see, you can write, that's not wrong, but when nitrito you have written, it means it is understood that nitrogen is a donating atom.
Yes, sir.
Right. Understood? So these are some bridging group ligands, okay, not important, okay, but I have given you a bit of test of it, like if you get, you can easily do this with the help of options, right? But I haven't seen the past 5 years they have asked questions. Okay, fine. So next is, we'll start the bonding in coordination compound, okay? How the bonding takes place in coordination compound. We have half an hour, so we can go with it. Fine, so write down next, bonding in coordination compound. There are different theories for this. Like we have in normal compounds, I told you BBT, hybridization, molecular orbital theory. So here also we have different theory. Okay, we have valence bond theory here also. Werners Coordination Theory we have here, right? We have crystal field theory, splitting of orbitals. There are many things, okay, that we are going to discuss here. So bonding in coordination compound. So the very first attempt to explain the bonding in coordination compound is done by Werner, and we call it as Werners Coordination Theory. Okay, write down into this. It explains the property and structure of various coordination compound one second. Yeah. Write down. The main postulates of this theory are okay, the first point you write down, according to Werners Coordination Theory, the first point in this first postulate, every element metal means every element two types of valencies. Two types of valencies. That is, we'll have a primary valency, and first you write down 2 points into this primary valency, and we also have one more. You can write down 3-4 lines. After 3-4-5 lines, you can write down secondary valency. These are the two valencies we have in coordination complex, primary and secondary. Write down primary valency. It corresponds to the oxidation state of the central atom. CMA, write down, central metal atom. It corresponds to the oxidation state of the central metal atom, and it is shown by a dotted line. Next point in this, you write down the primary valency is satisfied by the neutral satisfied by the negative ions. Negative ions such as Cl minus, SO4 minus, sulfate ion, etc.
Sir, negative?
The primary valencies are satisfied by the negative ions, Cl minus, sulfate ions, all those things. Okay. So in the complex, if the negative ion is present, those negative ions, only negative ions, okay, those negative ions satisfies the primary valency, and we represent the negative ions with the dotted line, because I have given you that it is represented by the dotted line. Okay, so negative ion is represented by dotted. I'll draw the structure also. Okay, secondary valency, you write down. It corresponds to the coordination number of the central metal atom or ion point wise. Write down. Okay, first point I've given you. Second point, it satisfies by either neutral molecules or negative ions. Either neutral molecules or negative ions. What do you like? What is the meaning of satisfies by? I'll discuss that in the last. First, you write down the notes. Satisfies by the neutral molecules or negative ions. Till now, you see the negative ion satisfies both kind of valencies, primary as well as secondary. Okay, next one.
Sir, can you repeat the first point?
First point. It
Yes,
corresponds to the coordination number of the central metal atom or ion. Right? So this one is coordination number. Okay, see this. This one is coordination number. But this one is the oxidation state of the metal, right? Second point I said, satisfies by either negative ion or neutral molecules. It is satisfied by only negative ions, okay? It is represented by solid line like this. This one is represented by dotted line like this. Write down. It is represented by thick lines or solid lines, you can write. Next point. Secondary valency are directional. I did not give you this point there. Okay, fine. Write it down. This is directional. You have to place this in a fixed direction, okay, with a fixed angle. Secondary valencies are directional. Primary valency is non-directional. Non-directional. This one is directional. And because of this only, the isomerism is possible in coordination compound, okay? Because you have to place the atoms, ligands around the central metal atom in a fixed direction at a fixed angle. That's why it shows isomerism. One more point here is this primary valency. It is because of the ionic bond. It is the ionic bond. The primary valency means the ions which are involved. We have ionic bond here in primary valency. But in this one, we have coordinate bond. Secondary valency, we have coordinate bond. Yes, right. Non-ionizable also, you can say that.
Sir, you said that primary valencies are satisfied only by negative ions, no, sir?
Yes, right.
Sir, but then in complexes like K4FeCN6 or something, potassium, which is positive ion, is satisfying the primary valency, no, sir?
No, it's not like that. I'll take one example, Tripan. Few minutes. Okay, I'll take one example.
Okay.
Okay. Next. See, because of this directional in nature, so those ligands which satisfies the secondary valency, you have to place this in a different direction, in a fixed direction, and that's why we'll have a coordination polyhedra. You have a shape of it, right? That we call it as tetrahedral geometry or square planar geometry and all those. That comes because of this directional nature of secondary valency. Okay. Now, these are the few properties you should keep in mind, that primary is ionic bond, oxidation state, non-directional dot line, secondary valency is coordination number, coordinate bond, thick line, and directional in nature. Now, we can understand this with one example. I'll just write down this example here. Suppose I'm taking an example of CONH3 6Cl3, this one. Okay. Could you tell me the primary valency for this one? What is the primary valency? What is the secondary valency? What is primary valency? We have to check oxidation state. Check the oxidation state.
Primary is 3 and
CL3.
secondary.
Sorry?
Maybe 3. Primary is 3 and secondary is
Primary is 3 because oxidation state is 3, right? So primary is 3 and secondary valency is 6 because the coordination number is 6. Like this, you'll get the primary valency and secondary valency. Now, if you want to draw the structure of it, the structure you can draw this way. You have cobalt in the center, and we have 6 NH3, and this satisfies, this is a neutral molecule, and this satisfies the secondary valency because secondary valency is 6 only. 6 molecules satisfies this, right? So we have 6 NH3, which is represented by the thick line 1 coordinate bond. This is 6 NH3, okay, by the thick line. This 3 chlorine, which is present outside and ionizable, this is, because this cannot ionize, we cannot break this complex, right? This is ionizable. So it is represented by the dotted line, which is this. 1, 2. This is this molecule. Primary valency and secondary valency. Now, what I'll do one change in this. Suppose I am taking this one. CONH3, CONH3 5 Cl and then Cl2. Number of, in this molecule, number of ionizable chlorine atom is what? Is 3, which is outside the complex, right? It's 3 only. In this one, again, if you count the primary valency is the oxidation state, that is 3 only, right? And secondary valency is again 6, right? So it is same here. This chlorine is a negative ion. It has a dual role here. It satisfies primary valencies as well as the secondary valency, right? It has a dual role. And number of ionizable chlorine atom is what? Tell me guys, number of ionizable chlorine atom?
2.
Chlorine atom is 2. The ion which is performing dual behavior, that is not ionizable because it is inside the square bracket. We cannot ionize the chlorine atom which is present inside the square bracket, okay? The number of ionizable chlorine atom is 2. Fine, chalega? Did you get it? Now, when you draw the structure of it, so how do we draw it? You see, we'll take cobalt here in the center. I'll just write down a line here like this, okay? NH3, NH3. Consider this as the coordinate only. NH3, we have only 5, right? So we'll have this and one NH3 here, 3, okay, then 4, and then 5, and here we have suppose one chlorine. So dotted line is for primary valency, chlorine, and since the chlorine atom satisfies both valencies, so there is one thick line also, means it satisfies both valencies, and then we have one primary valency here and one primary valency here. This one satisfies both valency. Write down here. Satisfies both primary valency and secondary valency. Understood?
Excuse me, sir.
Yeah.
Sir, in the first structure, while writing the chlorine atoms, does it how should we know between which ammonia molecule should we write the chlorine and all?
Anywhere you place, it is non-directional. It doesn't matter.
Okay, yes, sir.
Wherever you feel like, कर दो वहाँ पे, कुछ नहीं चाहिए. It's non-directional, no. So there's no way, like no, कहीं भी लग सकते. But for this, it is important, and because of this only, it has octahedral geometry. इसलिए देखो मैंने इसको octahedrally place करने की कोशिश किया है, right? Square and then one top and one in the bottom, right?
Yes,
These
sir.
are the structure we are trying to draw. But yes, the dotted line you can place anywhere, not a problem. Understood this one? Now I'll take one more example in this same one. This one you see. CO, NH3, 4, Cl2, and 1 chlorine atom outside. So if you count here, the primary valency is again 3, and secondary valency is again 6 here. And the structure is 1, 2, 3, 4, 4 NH3, and we have 2 chlorine atom which has the dual role, right? So 1 chlorine and then 1 chlorine will have. So number of ionizable chlorine is only this one, right? Let's say I will circle it. Ionizable chlorine is only this one. Correct? We'll take one more. The same thing, we'll place all the chlorine atom inside. CONH3, Cl3, like this. So here also we have the same thing. Primary valency is 3 oxidation state. Secondary valency is coordination number. When you draw the structure here, the structure is this. CO, NH3, NH3, and chlorine is here. 1, 2, 3. Dual behavior. So both lines will draw. Chlorine, chlorine, and chlorine. And none of the chlorine atom is ionizable. Number of ionizable chlorine atom is 0. Number of ionizable chlorine atom is only 1.
So the chlorine and NH3 have to be alternate.
Sorry?
So the chlorine and NH3 have to be alternate.
No. See, don't try. See, just to try to understand that how do we represent secondary and primary valence. इस structure को भी ignore कर दो. Structure will do once we finish the valence bond here. वहाँ पे हम लोग देखेंगे what is the hybridization we are getting, and according to that, what should be the geometry and what is the placement of this thing, ligands. Okay.
Yes.
ये coordination number is 6, and coordination number 6 का geometry is octahedral. that I'm telling you. Okay, कैसे होता है, we'll discuss that. Okay, so
Yes, sir.
tetrahedrally, like octahedrally, you have to place. That is it.
Yes, sir.
Okay, so this is the structure. Now K4FeCN6 may we have 6 cyanide ion, right? So 3 the oxidation state is 2 triple.
Yes, sir.
तो दो साइनाइड आयन जो होगा वो डुअल बिहेवियर होगा.
Okay, sir. Understood.
Got it?
Yes, sir.
Okay. Now on this one last thing we'll discuss. Okay. अब इसमें एक question like they ask about the molar conductivity of these ions. ऐसे करके they'll give you 4 or 5 options and they'll ask you to arrange them in molar conductivity. Molar conductivity, we know it depends upon what? It depends upon the number of ions, correct? Number of ions in solution, right?
Conductivity.
So we'll see how many ionizable chlorine atom is there, correct? The first one, how many ionizable chlorine atom, how many ions will get in the first case? This one? Achha, after this. How many ions will get in the first, in this case, you see, in this case?
4 ions.
We'll get 4 ions. Correct, because we have 3 Cl minus and 1 this wala complex. Correct. This positive and this 3 Cl. 4 ions will get here. Here we'll get 3, and then you can count the others also. Right. So the molar conductivity will be maximum for this one, then this one, and then we can go for the other 2. Did you get my point? Right. So number of ions you count, according to that molar conductivity you can compare. They can also give you like this one, it reacts with AgNO3, like देखो ऐसा कुछ हो, plus AgNO3. So in which of this the precipitate forms, or where we get the maximum precipitation? So here we get 3 moles of AgCl precipitation. Here we get only 2 AgCl, then only AgCl. In the last one we have no precipitation. So precipitation based question also they ask in this. You just need to keep in mind the ions which are present, atoms which are present outside the square bracket are ionizable, and according to that only we consider the reaction or the number of ions that we get in the solution. Understood my point? So this is the coordination theory. He said what? That there are 2 types of valencies and neutral ions. He talks about oxidation state, coordination number, and many things. But there are a few drawbacks also in this theory. He could not explain why the secondary valency is directional, right? The optical properties of molecules he could not explain. That's the one drawback. Okay, it's right on the drawback of Werners Coordination Theory. The drawback of Werners Coordination Theory. He could not explain the magnetic and optical properties of the complex. The magnetic and optical properties of the complex. Okay. Main drawback is this only. One more drawback was there, that he again could not explain why only certain elements shows remarkable properties towards forming the complex, the coordination complex. Okay, but the main thing is this only. He could not explain the optical properties, means why the secondary valencies are directional. He could not explain that, and the magnetic properties, means obviously there are a number of electrons, unpaired electrons were there, right? So now to overcome these problems, these drawbacks, we got another theory. That is, we have after this valence bond theory, VBT. Then we have crystal field theory, right? CFT, ligand field theory we have. Okay, molecular orbital theory also we have into this one. So there are many theories after this. Okay, but our syllabus is we have to do only VBT and CFT, that is valence bond theory and crystal field theory, right? So after valence bond theory, you'll be able to understand the structure of the molecule. Hybridization kya ho raha hai, and according to that, what could be the structure of the molecule, and how the elements, the ligands are placed around the central metal atom in order to gain the structure. Okay, so this VBT we'll discuss in the next class, right? We don't have time now. I can't start it. Right. I would request all of you that chemical bonding, I have explained the valence bond theory, that you must go through once before the next session. Understood, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. So we'll wind up the session here. See you in the next class, guys. Thank you.
Thank you, sir.
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 Thank you, sir.